Lesson 20, lesson 21. Section 7.3, we're going to continue with the operations on vectors. Now, in this section, we're given that v is a and b, w is c and d, and these are two vectors where k is some number. Okay. Now, remember from this image over here that this vector can be started anywhere on the coordinate plane, just likewise with this. Okay. Now, this right here, and they're going to use this notation sometimes. They'll use the notation I used in the beginning, which is right here. Okay. That's the magnitude of that vector. So this right here is denoted as the magnitude, okay, of that vector. Now, mathematically, it automatically tells you what it is. The magnitude of this vector is simply the square root of a squared plus b squared. Now, that looks familiar to me. That looks very familiar to me. I'm thinking Pythagorean theorem. I'm going to hold on to that thought, and we'll look at it in terms of the examples that we're going to have to do. Okay. V plus w, the addition of these two vectors, is the vector a plus b plus the vector c, comma d, and it's equal to the x value coordinates, a and c, added together, comma, the y value coordinates added together, b plus d. Okay? So that's not actually that difficult. Vector times what we would call a scalar, a constant, okay? This constant k actually distributes in and multiplies by everything. What we call this is actually something you would call a transformation of a dilation, okay? It takes the vector, it takes all these values, and it increases all of the values, x and y, by the same amount, or it decreases them by the same amount, okay? So it has a relationship there. Well, let's go ahead through this mathematically. This 8a asks us to find the length of w. Again, what is the magnitude of w? Well, w is this vector right here. Okay. Let me plot that point, best of my ability. 1, 2, 3, 4, and down -1. Okay, that point has been plotted. How would I find the length of the vector that goes from here to here? Well, I said back up here, that kind of reminds me of Pythagorean theorem. If you notice, I'm going to draw this in red. That's the x value. That's the y value. Hey, look! I created a triangle. Okay, this piece being 4, this piece being -1, and we're not doing any new work. We've done this problem 100 times before. It just happens to be in a different visual representation. A line with an arrow at the end of it. Okay, so what's the length of this vector? The length of this vector is going to be equal to, again, I can use this notation as well as that one. Doesn't matter which one, they're both the same. The square root of 4 squared plus a -1 squared. So this is going to be 16 plus 1 in the square root, which is the square root of 17. That is the magnitude of this vector. We are done with that problem. Okay, how about v plus w? Now graphically, remember, we'd create the parallelogram, u plus v, and then we draw that line there. There's an easier way to do this. With these values that were given, okay, v being -2, 3, and w being 4, -1, all I have to do is add their coordinate pieces. So the x's added together, the y's added together. So I'm going to write this out in detail. This is -2, 3 plus the vector 4, -1. And all I'm doing is I'm replacing this with a single vector being -2 plus 4, the x coordinates added together, comma, 3 plus a -1, the y coordinates added together. And then this thing is equal to 2, 2. This is the actual vector. If I were to plot both of these vectors on the coordinate plane from one tail end to the head end of the other, you will see that the vector overall just ends up being 2, 2. Okay? Which is really just this vector here, 1, 2, 1, 2, there. Just happens to be sitting in a different location. Okay, this is the vector 2 comma 2. Okay, and again, notice the notation again. These are not parentheses. These are pointed brackets. Let's go ahead and look at C. C is a negative 3 times V. Well, I'm going to write down what V is real quick so I don't forget it. On the previous page, it's negative 2 comma 3. So if I'm doing negative 3 times that, negative 3 times V is really a negative 3 times this thing. Now, let's recall in detail, what does this do? A multiplication by 3 takes the entire vector, okay, and makes it 3 times, and yes, I'm doing this on my paper, as long. That's what it does. The 3 says take this vector, multiply all the values by 3. So I'm going to go up to here as 2 iterations and the third iteration. So this whole thing, that one whole thing, is 3 times that vector. Okay, but in this case, this vector is a little bit different. So it's 3 times that vector. But what does the negative do? Well, if you remember back to the previous page, the first page, what does the negative on the negative vector do? Well, it just flips it around, makes it go in the opposite direction. So if this vector here, I'm playing with on this paper, if this vector was a negative 3 times that vector, it'd be this whole length, but going in what direction? This direction. Okay, a complete 180-degree rotation. So let's go back to this page here and mathematically show me what this is. Mathematically, all I'm doing is I'm taking this negative 3 and I'm distributing it in. So this is the vector. What's negative times negative? Positive. 3 times 2 is 6. Negative 3 times a 3 is a negative 9. Okay, that's what that vector is. Here, I'm going to do the exact same thing. Okay, I wrote down V, I'm going to write down W as well. W is supposed to be 4 comma negative 1. Okay, so in this problem, I want 2 times V, so 2 times a negative 2 comma 3, minus a 3 times my W, 4 comma negative 1. I'm going to distribute this value in, I'm going to distribute this value in, and I'm going to get this as a negative 4 times, comma 6, and minus a 12, comma negative 3. What do I do with the coordinate points here? I add the x's together. In other words, I'm going to do negative 4 minus 12. So it's going to be negative 4 minus 12, which is a negative 16. And I'm going to do 6 minus a negative 3, which is really just 9. And that is the new vector. Okay. Algebraically, that's what's happening. Physically, visibly, we've already been able to deal with those. Okay. Now, this next section of material, and I'm actually going to keep going. I'm not going to go ahead and create another video. I'm going to see if I can finish this in the time that we have. A unit vector. What is a unit circle? A unit circle is a circle with what? The radius of length 1, right? I'm going to draw that picture right there. Unit circle. Well, what's a unit vector? A vector with magnitude of 1, right? Shouldn't change anything, okay? Now we have 2 very specific unit vectors. We have I, and yes, this is similar to the whole I equaling to the square root of negative 1, but it's not that. It's not that. Vectors, I stands for the unit vector in the x direction, okay? J stands for the unit vector in the y direction. Okay? So, find the unit vector in the direction of this, then write the vector using this. Okay? So, what is the unit vector in the direction of this? Now, what do I have to do? This vector has a certain length to it. Okay? What is the length of that vector? Okay? The length of that vector is equal to the square root of negative 4 squared plus 2 squared. Yes? That is the length of that vector. Let's go ahead and find out what that length is. That length is going to be the square root of, this is going to be 16 plus 4, which is the square root of 20. This is the length of that vector. Okay? So what is the unit vector that's headed in that direction? In the direction that's equivalent to this? Well, remember, back here, multiplying a vector by a constant doesn't change the direction unless that constant is negative. If this is the length of the vector, how can I eliminate that length? How can I make this a length 1? Well, why don't I just take the vector and divide it by that length? Again, a unit vector in the same direction, okay, will always be equal to the vector itself divided by the length of the vector. I'm taking the vector, has a direction and a length, and I'm removing the length from it. I'm dividing it by the length that it is. So let me go ahead and do that. This thing is really going to be equal to a negative 4 divided by the square root of 20, and a 2 divided by the square root of 20. That's it. This is the unit vector. It's got length 1. If you don't trust me, square this, add it to this squared, take the square root of the whole thing, you'll get 1. Okay, you will get 1. In the direction of that, that's the first part. It says then write the vector using I and j. Okay, now there's two different ways I can do this. What I'm going to do is I'm going to write the original vector using I and j. V is equal to this vector, negative 4 comma 2. The notation using I and j is I have negative 4 in the x direction, 2 in the y direction. I have negative 4 of these in the x direction. It's negative 4 i's. Negative 4 of these things in the x direction. I have a positive 2 of these things in the y direction, so plus 2j. These two things are exactly the same. Heck, this is almost the exact same as this one as well, except for this is unit length. These are all headed in the same direction. These just have a different length. These have a length of radical 20. Okay, this one has a length of 1. So very carefully consider what we have here. Again, consider what we have here. These are just two different notations of writing the same vector. Sometimes you'll see it this way. Sometimes you'll see it this way. If you don't like it this way, just change it. Negative 4 of the x's, 2 of the y's. I just changed it back to that. Okay. Last piece, multiplication of vectors. We actually have two different forms of multiplication. Okay. There's something we call a dot product. There's something we call a cross product. Now, in this section of material, we're not going to actually deal with the cross product. Okay. Later on in mathematics, specifically linear algebra, the cross product will come back around. But we denote the dot product, the dot versus, the cross. There are two different multiplications. Okay. We denote the dot product as v dot w is the same thing as the x coordinates multiplied together plus the y coordinates multiplied together. That's it. That's what the dot product is. So when I ask you to find the dot product of v and w, what is the dot product? The dot product is going to be a number. Keep that in mind. Okay? The multiplication of two vectors under the dot product will be a numerical value. That's not true for cross product. That actually gives us back a vector, but we're not worried about that. We're not going to do that in this class. So, what's the dot product? The dot product is 6, negative 2, dotted with negative 3, comma 4. And what do? I multiply the x coordinates, 6 times the negative 3, and I add that to the y coordinates multiplied. Okay, so this is a negative 18 plus a negative 28, which is the same thing as a negative 46. That's it. Okay, now why is this important? In terms of the values that we get back from the dot product, okay, there is a specific thing as to why it's important. And if you want to know, you can ask me in class. In terms of needing to know it, you really don't. Okay, all you need to be able to do is show me what the dot product of two vectors really is, numerically.